Here is a wrist brace limited range of motion in the flexion extension axis. In the radial ulnar deviation. Here is a normal range of motion in the flexion extension axis. And in radial ulnar deviation. Here is what a trial for recording the range of motion looks like for the flexion extension axis. So I'll go ahead and start it. And at first, the open wrist will return to a neutral position. And from this point, with a visual aid, we have 20 seconds to get our maximum and minimum joint angles in the flexion extension axis. You can see I'm trying to move as far as I can in that axis. Well, now the 20 seconds are up, so it goes back to neutral, and it tells us what our max and minimum angles are. So now showing the wrist pointing task with fixed target placement in the flexion extension axis. So I'll go ahead and begin. The open wrist will turn to neutral, and now we can see that targets are placed away from the center. After each away from the center target, there will be a target returning towards center. So you just move in the flexion extension axis to meet these targets. If I wait 6 seconds and I fail to achieve the target, we'll move to the next target, which was there at the center, actually just hit it, and then skip to the target beyond that. For the scaled placement, essentially what happens is visually the targets are placed the same distance, but depending on the range of motion that you input, recorded during your range of motion trials, the actual displacement of the cursor here, this red dot that corresponds to my flexion extension and radial ulnar deviation angles, will change inversely proportional to the range of motion that I input. So the higher the range of motion that I achieve, the slower this will move, and the lower that I achieve, the quicker that it will move for a corresponding input through the encoders from the open wrist.